just want to thank the organizers for inviting me. I'm very pleased to speak to you today. Very pleased to be at this conference and see so many familiar faces. I think I've kind of given up on being able to say hello to everybody that I want to. It just seems like an impossible logistical task. So, hello. But I would still like to talk to you all individually if I can. We'll see if it happens. But I should also, I feel it's fair that I should warn you that there will be no jokes in this talk. There won't be any corollaries of any kind. So with that, let me go on. So I actually want to stay on the opening slide for just a moment. In mathematics, we like theorems, and we like proofs. Even ugly proofs of theorems are nice because we like the theorem so much, or beautiful proof is better. We might like that proof for its own sake. I don't know if any of you are like me. I like definitions. Really like a definition. But you can't publish a paper on a definition. Hey, isn't this a cool definition? Right? You can't really give a talk on a definition. You have to have some reason that this definition actually makes sense. So really, in some sense, my favorite part of this talk is the definition. And I will also do some things that justify this. The definition was sort of thrust upon me because I was working on something else, although I wish I just come up with it just because it was cool, whatever. So first of all, let's talk about linear algebra. Nothing surprising on this slide. It might not be the way that you thought about linear algebra, but you can think of it as the study of linear relations. So if you just take formal finite formal linear combinations of vectors, say in Rn, and you can think about having a way of evaluating it. If they evaluate to 0, we'll call that a relation, linear relation. And you can formulate linear algebra that way, right? A subset is independent if there's no non-trivial linear relation, and a subset is spanning if, well, for every vector, for any vector that you, in Rn, say, there exists a linear relation of this one, that given vector, and then you write it basically as a linear combination. Okay. And you can also say the same thing about linear maps. Again, this is not the way we usually define linear maps, but it's a linear map if and only if, for every linear relation, if you apply the map to each vector in the relation and keep the same constants, you still get a linear relation. It sort of seems like too much to say to define a linear map, but that's a linear map. So what I'd like to do to start out with is to talk about something I'm calling partial linear structures. So let's just distinguish a subset of the linear relations. And I'll just be working with Rn. So just think about linear relations on Rn. We'll call it the subset A for active or something. And we'll just reformulate linear algebra in terms of this subset of the linear relations. So, all right, so you can say that a set is independent if there are no non-trivial active linear relations. And again, actives is just this set that we've just decided on. A set is spanning if every vector in Rn, for every vector in Rn, you can find an active linear relation of this form. Exactly, it just says that I'm writing that given vector A as a linear combination of other vectors. And finally, and this is the thing we'll be thinking about most, a map from Rn to Rm. But now I'm not thinking of Rn in the usual way. I'm thinking of it as this partial linear structure where I've distinguished a set of relations on Rn, and to distinguish a set of relations on Rm, and I'll say that this map is linear if, for every time you have an active linear relation, in other words, a linear relation that is in A, and you act on it by this map, in other words, take every vector in Rn, every vector appearing in the linear relation, and act by this map, that you get something that's not just a linear relation, but actually an active linear relation in Rn. Okay? So one could do this. Right? So a couple comments. First of all, if you put some conditions on this, maybe we don't just let ourselves take any set of active linear relations, but if you put some conditions, you can show that the basis exists. The conditions are if the proof that every vector space in the completely abstract sense has a basis using Zorn's lemma. You just put the conditions on that make it possible to modify that proof, and then that's good. So if you sat down, in fact, if you're bored, sat down for the next 10 minutes and figured out, you went through that proof again in your mind, you would get exactly the same conditions I would. I'm not going to talk about those conditions, but the other thing is, this level of generality, although I actually think this is a cool thing to think about this way, this level of generality I can't really sort of defend necessarily. So really, the reason I wanted to start with this level of generality is just for clarity. I want to make sure it's clear what we're doing. Because there's going to be a very specific set, or specific kind of example where we're choosing this set, script A, of active relations in a specific way. And that's what I'll mostly be interested in. Okay, I should also say, if anybody has seen anything like this in this generality, I would love to hear about it, because, somebody famous that I should remember said 2 examples make a theory, and I've only got 1. So how are we today? Is the bottom of the screen now visible now that we've reconfigured things, or is the lectern still in the way for some people on the left? Is it good? I'm seeing, Jim, I think you might be the extreme point there, almost. Okay. So we're good, good. And I won't have to do strange contortions to get the bottom up. So we're going to start with a skew symmetrizable integer matrix. Now if you're familiar with Cartan matrices, they're symmetrizable. And this is skew symmetrizable in exactly the same sense. And if you're not familiar with either of those notions, then just you can pretty safely think of a symmetric matrix. Skew symmetric matrix. And I'm going to call such a matrix an exchange matrix. So let's take, in addition to that matrix, an additional vector in Rn. It's an n by n matrix. I'm going to take an additional vector. I'm going to make another matrix by just putting that extra vector on as a new bottom row. And now it's got n plus 1 rows and n columns. Okay. So this is a definition you've seen in connection with cluster algebras if you've seen the definitions of cluster algebras. But I want to go through it somewhat slowly because it's somehow at the heart of what we're doing. So if I choose one of the integers from 1 to n, in other words, one of the indices that indexes a column, indexes the first n row. So I can mutate in that direction. And here's how I do it. Well, if you're like me, you don't process mathematical formulas quick enough to follow things like that at talk. But this is what you do. So if I'm going to mutate this matrix, does the bottom row look red today?
Yeah.
Okay, good. Slightly red? Slightly red will have to do. So if I'm going to take this matrix, my bottom row, my vector A, is these vectors here. I'm going to mutate in row on index 3. This is saying that if I'm going to change every entry, or perhaps leave it the same. If I'm going to change if I'm looking at the entries in the 3rd row or the 3rd column, all I do is negate them. Okay, so if you look at the matrix on the right, negate the 3rd row and the 3rd column. Entries outside of the 3rd row and outside of the 3rd column, what I do is I sort of want to look from there, let's say right here. If I'm looking at this entry, I want to look into the 3rd column and look into the 3rd row from there. And I'm going to look at these 2 entries. If they have the same sign, then I'll multiply them together and add them, but with the sign they have. So in this case, this entry doesn't change because I look and I see the 2 and the -1 opposite signs, so I get it still 0 there. But for example here, if I'm looking at this one, I look into the 3rd row and the 3rd column. These 2 have the same sign, and so I'm going to multiply them together. -1 times -3 is 3, and I'm going to, but since they were both negative, I'm going to subtract them rather than adding them. So this 3 becomes a -3. Okay, and the whole matrix, every entry you do that. Okay, so and finally, we might want to do this lots of times. So maybe I won't just choose the 3rd index. Maybe I'll choose the 3rd and the 4th and the 1st, and etc. Any sequence of indices, I could do a sequence of mutations. It's exactly the same thing, just repeat it at a different index at each time. Questions about that? Okay. Just continuing the same notation, this extended square matrix extended by 1 row and a sequence of indices. I can define a map. What I'm going to do is I'm going to just, I said coefficient row. See, it's hard to keep the jargon from creeping in. Coefficient, this final row. So I'm going to take my matrix with the initial B and an A at the bottom. I'm going to mutate according to some sequence of indices, and then I'll read off the bottom row. And that's a map. Okay, so I have a map from, whether the input is whatever vector I put in on the bottom row, the output is whatever I get after doing the mutations. Okay, so specifically, if I take just one single index, right, the map looks like this. Okay, and again, this is more than I like to try to digest sitting in a room. But the thing that I'd like to point out is, this is telling us what the jth index, the jth entry of my new vector is. It depends on what the kth entry is. K is the place where I was mutating, the index on which I'm mutating, and what I do depends on what the kth entry was, whether it's non-negative or non-positive. And it's linear in the part of Rn where k is non-negative, and it's also linear in the part of Rn where a is non-positive. Okay? So, certainly this map that I'm describing here was for one mutation is a piecewise linear map, two pieces, two half spaces. And if I do some sequence of these, it's going to certainly be piecewise linear. It's going to be a homeomorphism of Rn. And also you can check if you want that the inverses to these homeomorphisms are mutation maps of a different sort, starting with a different B. Okay. So let's just do this example. If I start with B being this matrix, it's skew symmetric actually, and I mutate in direction 1. So what am I supposed to do? So I'm supposed to negate the first row and column. I do that. A1 becomes minus A1. And then what goes in here? Well, there's nothing really interesting along the diagonal. Those will always remain zeros. What goes in here? Well, if A1 is less than or equal to 0, then A1 and 1 have weakly different signs, and so I'll do nothing. Right? And I only do something if they have the same sign. If one is 0, it doesn't. I still don't do anything. So if A1 is non-positive, then I'll just have A2 in here. Okay? But if A1 is non-negative, I'll actually have A2 plus A1. Right? I'll multiply 1 times A1 and add it to the A2. Okay? So what this is saying is on the right half plane, I'm doing, sorry, let's start with the easy one. On the left half plane, I'm just doing a reflection. On the right half plane, I'm doing a reflection and also a shear transformation. Okay? So that you can see that the R gets deformed according to some shear. Okay. So now we're getting to the main definition, I guess the main piece in the main definition, a B-coherent linear relation. So I'm going to take just really, I guess, a finite set. What I want to get to is right here. I'm going to take a finite formal linear combination of vectors. Indexed by a finite set, indexed by a finite set. And it will be a B-coherent linear relation if, well, no matter which mutation map I apply to it, if I evaluate it to 0. So this is an infinite number of conditions, right here, because this subscript k is any sequence of mutations. So I'm saying that for any sequence of mutations I could apply to every vector in this linear combination, after I evaluate it, it still remains 0. Okay? So in particular, I could apply the empty sequence, and that means that this thing has to be a linear relation in the usual sense, but it has to be much more than that. Okay? And I should, since you can all see the bottom of the screen, I guess I have to mess up. I'm sort of fibbing about this definition. If B has a row of zeros and equivalently a column of zeros, then I have to do something slightly different, but we won't worry about that. Okay? You can take care of that problem basically by thinking about the irreducible case in some sense. So this is what a B-coherent relation is. And this, you can see what we're going to do next. We've defined some special subclass of our linear relations. And so we can do mutation linear algebra. So I'm going to write just a little bit of more notation here. R to the B. Now you might think that that's like an n squared dimensional vector space, but I don't mean that, right? R to the B. B is an n by n matrix, and so I really mean Rn. Okay, so Rn, but I'm writing the superscript B to tell you that I want to use the partial linear structure given by B-coherent linear relations. And I need that because I'm going to be pretty soon having a B and a B prime. So I need to be able to tell you which partial linear structure. But if I consider the partial linear structure, where the active linear relations are these B-coherent linear relations, then I'll say that I'm doing mutation-linear algebra. So let's just, this is really just review of what we talked about, except now with much more definite terms in here. So a set is independent in the sense of mutation-linear algebra if there are no non-trivial B-coherent linear relations that are supported in that set. Okay? A set is spanning if, for any vector in Rn, I can find a B-coherent linear relation that writes it as a linear combination of other vectors. But that has to be a relation that stands up under all these mutations. Okay, so what I'm not going to talk about is something that's very much related to cluster algebras. And it really just saying words here, but if you find a basis for this reals to the V, this mutation linear space, then what you've really found are universal geometric coefficients for cluster algebras associated to B. And I should say, you know, the conference is named FPSAC, so this is really a stretch. The place where formal power series come into this talk is that in defining what I mean by universal geometric coefficients, which I'm not going to do here, but in defining that, I need to at some point put a topology on a possibly infinite dimensional vector space. And when that is a countable dimensional vector space, then the topology I'm using is the formal power series topology. So there it is. That was the FPS. So, because that's what I'm not going to talk about. What I am going to talk about is mutation linear maps. Okay, so just going along with the definition that we had before, a map is mutation linear if, well, for any B-coherent linear relation, if I apply, my map is eta, so for any B-coherent linear relation, the expression that I get by applying eta to every vector in that relation is a B-prime coherent linear relation. So I'm talking about a mutation linear map between two different partial linear structures, two different mutation linear structures, you could say. Okay? So this would be a good point for questions. Actually, any point is a good point for questions. But anything? Yeah, Jim.
So what are you assuming about the nature of the map eta?
Just this, but it's going to, so pretty soon I'm going to sort of restrict B to sort of a well-behaved case, and I don't know how far well-behaved goes. Maybe every case is well-behaved, I'm not sure yet. But in a well-behaved case, eta is going to have to be piecewise linear. It's just going to be forced. I mean, if strange things happen that I can't quite rule out yet, I'm not sure what it means. Yes?
If I were to think of like one good running example in my mind whenever I see B, which B should I be thinking of?
You should think of the one that was up there before with the 1 and a -1, and it's going to come up as soon as I do this.
Thank you.
So, that's exactly the right question. Okay, so this is the picture you saw before. This is what the mutation map does to R2. The mutation map in the first index. There's another mutation map. Oh, sorry. There's another way to think about this same mutation map, and then another mutation map. So if I just, and I'm happy that colors are working today, because there should be 5, well, I guess 6 if you count the black, different colors in these pictures. Tell me if there's not, and I'm not sure what I'll do. So if I just decide, not really arbitrarily, to break up my R2 into 5 two-dimensional cones like this, then I can describe sort of pictorially in a different way what this mutation map does. Remember, on the left half plane, it just acts as a reflection to the right half plane. And on the right half plane, it was this shear, the reflection and shear. So that's going to take the white to the white, and the gray to the gray, and then blue to the blue. Okay? So the other mutation map is similar, except it's taking upper and lower because it's acting on the second index somehow, or it cares about the second entry in the vector, whether it's positive or negative. And so it's going to do a similar thing down here. It's going to take the red to the red, and the white to the white, and the gray to the gray, etc. Okay? So the other thing that happens, and this is the part that's, I hope, been not confuse you about. When I do either of these mutations, remember that I'm supposed to change the sign in the first, in either the first row and the first column, or the second row and the second column. For a 2 by 2 matrix, that's the same, since there have to be zeros along the diagonal. It's skew symmetrizable. If it was skew symmetric, there would be zeros along the diagonal, so there are in this case. So really, in either case, when I do the mutation, I'm changing b to minus b. And so if I do the mutation at index 2 twice, I actually go back home, because it's a slightly different map. I'm not taking the lower half plane again and doing the funny thing. Now, to go back, I'm doing the shear transformation on the upper half plane. Okay, so let's think about, so if I'm going to take a sequence of mutations, a sequence 2, 2, 2, 2, 2 is not all that interesting. So the sequences that are interesting are 1, 2, 1, 2, or 2, 1, 2, 1, right? So when I'm looking at this, and since I've got the plane broken up into cones like this, you can start to see how sort of mutation linear algebra is happening in this case. For example, if I just follow along one of these cones, these two-dimensional cones, under a sequence of mutations, say 1, 2, 1, 2, right, the blue goes to the blue, if I do a mutation 1. And then, well, both of these that are top right and bottom left of the screen, both of those have the minus b as their mutation matrix now. So what I really should do, if I want to do the mutation in direction 2 from this blue cone, I should go down to here and look at the white cone. It's the same band. And now, if I go do the mutation 2, I go to the white cone here. And if I want to then do the mutation in direction 1, I go to the white cone here, etc. So, I mean, modulo permuting colors, we can just keep following that around. So, what does that mean? It means, for example, if I have a linear relation that lives entirely in the blue cone, then it's going to be B-coherent. Because, the map is linear on each cone, and I'll just be, taking this linear relation and applying linear maps to all the vectors in it, and that's going to still be a linear relation. Okay? So, from there, I guess each map is linear on each colored region. From there, we can think about a basis. Okay? Certainly easy to see a spanning set. The independence is something very quick that you'd figure out, but I won't talk through it. But why, so how do we easily get a spanning set here? If I take one non-zero vector in each of the black rays, then every vector in R2 is in one of these cones, and I can write any vector in R2 as a linear combination of my chosen, in this case, 5 vectors. And I can do it in a way that I'm writing it as a linear combination of 2 things in the same cone. So for example, if I take a vector there, maybe this is one of my basis elements, and that's one of my basis elements. That relation that writes that vector as a linear combination of those 2 is going to survive under all mutation maps. Okay, so that relation that writes my vector as a combination of those basis elements will survive. It will be what we call B-coherent. This is a good time for questions. If this was confusing, I would be happy to try and save it. Okay. So one of the things that's funny, this points out something that's sort of interesting and cool, I think, about the idea of partial linear structures. This is a positive basis. So not only can I write any vector as a linear combination of bases, as a B-coherent linear combination of basis elements, but I can write any vector as a positive, or as a non-negative linear combination of basis elements. And this makes no sense in normal linear algebra.
So I guess I did have a dumb question.
No, not dumb.
Well, we'll see. Is the number 5 predictable here? Are all bases going to have size 5 for some reason that I don't see?
The people in the room who do cluster algebras were expecting a 5, maybe. And it's a Catalan number in this case, and it's going to be. It's actually just a rank 2 thing. That's a Catalan number. Sorry. The number of these cones will be a Catalan number typically. Generally.
So what do you get if B is something more trivial like the identity matrix?
It can't be the identity matrix because it's got to be skew symmetrizable.
Oh.
So this is the most trivial. The most trivial example is just the 0 matrix.
Okay.
And then I'd have to tell you the true definition. Yeah.
Can you prove that every basis has the same size in some generality?
I have thought about that, and I'm not sure. So we're gonna see that bases can be infinite, even in Rn. Because, so it's so then same size gets complicated. I think it's probably true.
Do bases always exist?
So in the mutation-linear algebra case, yes. In the general partial linear structures case, you have to assume these assumptions. But you wouldn't want to build it without those assumptions. They're really basic assumptions. So, other questions? Okay, so the example suggests there's sort of an easy way to get mutation-linear relations. And that is, you're going to find vectors that are in the same domain of linearity of every mutation map, and then just make linear relations among them, and find vectors, find your basis by thinking that way. Okay, so let's talk about how you might make this fan in general. So first of all, this definition will start to make sense if you remember that the key point, sort of the pieces in the piecewise linear relation are you have to decide if you're on one side or the other of a coordinate hyperplane. So what I want to do is I want to say that two vectors are, I don't know, B equivalent or something, if no matter what mutation map I apply, their vector of signs is the same. Their sort of vector of strong sign. 0 is one of the possible signs, not just non-negative, non-positive. So if you think about two vectors that have that, if I keep mutating, they will always go the same way, and I'll always be applying a linear map, the same linear map to those two vectors. So I'll say B classes are the equivalence classes under this relation, and I'll say that B cones are the closures of B classes. Okay? And I can make a definition. The collection F sub B of all B cones and all faces of B cones is the mutation family. Okay? So I'm going to take this equivalence relation, which is based on the idea of trying to make these two vectors equivalent if they're going to be in the same linearity, same domain of linearity of every mutation map. Take the classes, close them, those give me my cones, and I have to also pass the faces to get a fan. But the theorem is that it is a complete fan, and it might be a complete fan in a way that you're not used to thinking about. It's a complete fan with possibly infinitely many cones. So complete sort of means weird thing. It can be complete because cones sort of limit, in the limit, fill up space. But that's a little different than you're thinking of if you're used to thinking of finite. So here's an example. So this example comes from that B matrix, and I have to show you what I'm telling you I'm showing you some fan. So what am I doing? So it's a three-dimensional fan, and if you think about just drawing a two-dimensional sphere about the origin, and then looking where each cone intersects that two-dimensional sphere, you haven't lost any information. So now what I have is a collection of spherical, in this case spherical triangles and arcs and points on the sphere. And that's a little better to look at than a three-dimensional fan, but let's now stereographically project it. So what's really happening, and I agree with Jim about the long sticks being better than laser pointers, although in this case, if you have to jump, that's also entertaining to the audience. But, I don't have to right now. So this place is sort of dense with cones, but it's the equator of the sphere where I'm doing my projection. Okay, so if you think about what's really going on, it's like the top of the sphere is coming out here. Okay, here's the equator, and of course stereographic projection means that the other side of the sphere is sort of being pulled out to infinity. So everything outside of this circle is going off towards the point of infinity. So the sphere and then the rest of the sphere should be sort of folded underneath. Okay, so that's what we're seeing. This is the fan. This B matrix is connected with Markov triples and things like that, and this sometimes is called. This has the name Markov attached to it somehow. I don't think Markov do this ever. Anyway, that's just an example of what a mutation fan could look like, and you notice that there are infinitely many. At least to suggest that there are infinitely many cones. So I need to just to go back to talking about positive bases a little bit, but you can let this definition leave your mind quickly if you want. A positive basis, a basis for this mutation linear structure is positive if you can write every vector as a positive, as a non-negative B-coherent linear combination of other vectors, of basis vectors. And so the theorem is that if there's a positive basis for your mutation linear structure, then a map is mutation linear. And it's actually, you have a positive basis for the domain of your map. A map from R to B to R to B prime is mutation linear if and only if for every B cone, in other words, for every cone in the fan for B, that the restriction to that cone is a linear map that goes into some cone in the fan for B prime. Okay? Again, don't worry about positive bases so much. Just think about this is the well-behaved case, and we're going to stay in the well-behaved case. And I'm going to now restrict my attention in 2 steps because there's something interesting to think about even for a very restricted case. First of all, let's think about bijective mutation linear maps. You can talk about mutation linear isomorphisms, but you can also talk about mutation linear maps that are bijective but not isomorphisms. It's sort of like, certainly linear maps on vector spaces that are bijective are isomorphisms, but it's not true here. It's more like posets in that way. You can have order-preserving maps. Okay. So bijective mutation linear maps, not necessarily isomorphisms. And let's even actually restrict to a very specific question. That is, when is the identity map mutation linear? Now, for it to even make sense, of course, B and B prime would have to be the same size as matrices. They both better be n by n. But now I'm talking about maps from Rn to Rn. And I just write B and B prime because I'm talking about 2 different exchange matrices. So the previous theorem says that the identity map is mutation linear if and only if there's a refinement relation between the 2 fans. So the fan where you're starting needs to be finer. Okay? Right? Because the theorem said you have to map each cone linearly into a cone for the other fan. Okay? So linearly is easy since it's the identity map, but it's just a question of refinement. So this can fail, and I'll show you in a moment where it fails. But the surprise is that it actually happens quite often. This is the point in the talk, I wish I could convey the sense of surprise that I felt when this actually worked. I think if you sort of really mucked around with cluster algebra type stuff, you would feel that same sense of surprise, I think. But for you, it's like, okay, he made a definition and something works, Okay, but it really is a surprise to me. One of the necessary conditions for this to happen is that there needs to be a domination relation between the 2 matrices. And this is exactly what you would maybe guess that word should mean. I have 2 matrices, and the signs of entries matter. So when I go from B to B prime, I don't want to change the signs. I don't want to change it from -2 into a +1 or something. But for B to dominate B, I want corresponding entries to weakly agree in sign and be smaller in absolute value in B prime. So we'll have an example of that in just a second. Take entries in my matrix, I'm not going to change their sign, I'm going to decrease their absolute value. And I've made a matrix that's smaller in this domination sense.
What's weak agreement?
What's that? Weakly agreeing in signs means I'm allowed to change something from positive to 0, and then I'll say they still weakly agree. That's a good question, I'm glad you asked. But that can't sort of strictly change their sign from positive to negative. And there is an asterisk here, necessary condition. This is in the well-behaved case. So this is actually a necessary condition. Okay, so let's do an example. We'll start with our fan that we had before, and this is where I really hope the red just really looks red. So up there, and actually, maybe I wish it were white. So it'll be white soon. But what we're doing is we're taking, we're going to take this matrix and we're going to actually do a lot of reductions. We're going to, what do we have to do? We keep the sign pattern the same, but we reduce some things in absolute value. So this 2, and that 2, and that 2, and that 2 will change the 1s, but keep the same sign. When I do that, and I draw the new mutation fan, I get something like this. Okay? And not being sure whether the color would work. I think you can kind of see that red, but if you can't, I'm going to sort of slowly fade out. So we're really refining that old fan to get that, and here's the new fan. Okay, and then can go a step further. You can only see what matrix we were working with when we're done doing it. But all right, so you can see exactly that we changed some 2s to 1s. If we change the remaining pair of 2s to 1s, a similar thing happens. This very infinite fan now becomes a finite fan. And this is a fan that, modulo not being used to thinking about stereographic projections, some people just don't like to think about stereographic projections even when they're used to it, but this is something that you might recognize. This is a dual fan to a polytope that's an isosahedron. I don't know if this is one of the standard realizations of the isosahedron, but that's an isosahedron, and that's not an accident. Okay, now you can see, now that we're done, you can see what we're actually doing. So here's a non-example too. If I start where I was at the end of the last slide, and just decrease one more pair of 1s down to 0s, I get these two fans that are just incomparable in the sense of refinement. It just doesn't work. So let me recap what we've done so far. If you didn't like most of the first part, it's mostly sort of piecewise linear algebra, piecewise linear geometry sort of from now. But so far we talked about mutation maps. It was some family of piecewise linear maps given by matrix mutation. We talked about B-coherent linear relations that are preserved by all of those mutation maps. Mutation linear maps send B-coherent linear relations to B-coherent linear relations. We defined this fan, common domains of linearity, and we're focusing on when is the identity mutation linear. Turns out that that's really a sort of a geometry problem about these fans. So a question of refinement between the fans. So what I'd like to do for the rest of the talk, I told you I like this definition. And what I'd like to do is, with as much time as I can reasonably use, tell you some combinatorics that attaches to this definition that I like and that I hope you'll like. And we'll see how far we get. So specifically, we're going to look at specific cases when this refinement relation actually holds. In finite type, in other words, this is maybe not the finite type that many people would, the way most people in the room who would define finite type would define it, but when this mutation fan is finite, and when the B matrix is acyclic. So if you think about the sign pattern, it's sort of defining a directed graph, and we need that directed graph to be acyclic. The mutation fan ends up being the dual fan to a generalized isosahedron, also known sometimes as the Cambrian fan or the G-vector fan. And in this case, sort of everything works. Whenever you have a domination relation between exchange matrices, you actually have a refinement relation between the corresponding fans. The refinement relations actually come from a lattice quotient relationship between Cambrian lattices. And I'll try to say a few words about what some of those words mean. And in fact, this is a hint of something else happening, which is that there's a lattice quotient relation between weak orders on different finite Coxer groups. So I'll also, just to give a nod towards motivations for thinking about a lot of this stuff, and talk about how there's an algebraic relation that's sort of suggested, an algebraic relation between cluster algebras that's suggested by this mutation-linear map idea. And hopefully say something about isosahedron fans, and there's no way in the world I'll ever say anything about triangulated surfaces, but that was the plan all from the start. I just get nervous about finishing early, so I always have all this stuff at the end. It's not going to happen. We might talk about isosahedron. So, let's go. So, Cambrian fans, and it would take a long time to define them actually, but before we get there, we need to point out that this exchange matrix thing is really hiding the information of the Cartan matrix. So if I have an exchange matrix for a skew symmetrizable, I can take all the zeros that have to be along the diagonal, turn them into 2s, and then turn every off-diagonal entry negative, or leave 0 to 0. So if I start with this B matrix, I get that Cartan matrix. Okay, so that's going to be a skew symmetrizable matrix with negative entries off the diagonal. So, skew symmetrizable matrix. If we're in finite type, it turns out that finite mutation fan is going to mean that this Cartan matrix is a finite type, so we have a finite Coxer group running around. We have a reflection arrangement. and in fact a very specific reflection arrangement given by that Cartan major. So there's something called a Coxeter fan. You take all the reflecting hyperplanes for this all the reflecting hyperplanes for this reflection group, I should say. Then it cuts space into cones, and the maximal cones are in bijection with the elements of the vial group. The Cambrian fan is a certain coarsening of the Coxeter fan. So you're taking all these cones that are cut out by hyperplanes and you're just merging some of them. And it depends on this extra information. See, when we went from B to A, we threw away information. We threw away the information about whether this was -2, 1 or whether it was -1, 2. You're free to choose. So if you put that information, if you consider that information, you get a certain fan called a Cambrian fan. And there's two ways to look at this. You can think about coarsening the Coxeter fan according to certain lattice congruence. Or you can think about coarsening according to the combinatorics of certain elements of the Coxeter group called sortable elements. Either one of these explanations would take a long time. So let's just leave it in this sort of vague sense, but we've got this coarser fan than the fan defined by reflecting hyperplanes. But this is something that's not completely unfamiliar, perhaps. If we take our Coxeter group to be the symmetric group, then we're talking about the normal fan to the usual icosahedron. And in more generality, you get generalized icosahedrons. So, so I think I said this already, but now on a slide. If B is a cyclic of finite type, then this mutation fan F sub B is actually a Cambrian fan. And there's a key technical point which tells you exactly how you have to identify the vector space where the Cambrian fan naturally lives with Rn. You need to make the fundamental weights be the standard basis vectors. But if you do that, you get F sub B out of the Cambrian fan. And the theorem is that, in fact, F sub B refines F sub B prime if and only if B dominates B prime. So this is, and again, I guess I don't say this on the slide, that means that the identity map is mutation-linear in every case where it possibly could be. So you can think about this, though, as a statement about refinement of Cambrian fans when we decrease edge labels on Coxeter diagrams. And let me do the example wrong first, because if you're thinking about, say, the case of a Cartan matrix of type B2 and a Cartan matrix of type A2, then you see already this couldn't possibly work. Just these two fans are incomparable, right? If I added an extra ray right here, this is a reflection arrangement of type A2, and if I added a couple extra rays, I get B2 there. There's just no way, they're incomparable. But if we do the example correctly and we identify fundamental weights with standard basis vectors, and sort of instead of drawing our pictures as symmetrically as we can, then it actually works. Okay, so this is a Cambrian fan of type B2, and here's type A2, and there's a refinement. Okay, another example. This is a Cambrian fan of type B3, and that's a Cambrian fan of type A3. Okay, so I guess since you can't see the B matrix, now that you've seen it. So you can see the refinement relation. The black, I guess, what are they? They're really two-dimensional faces that have gotten projected down to arcs. They disappear as leaving the red. Okay. All right. So I just want to say something, again, without even having defined cluster algorithms, but let me try to sort of make this, say something at least for people who are not familiar with that definition. If you're like me, there's a lot of definitions you've seen in talks, but, well. So the cluster algebra is generated by cluster variables, certainly not freely generated. There's a lot of relations among them. And it's true that rays in the mutation fan, and I'm definitely talking finite type here, but rays in the mutation fan are in bijection with the cluster variables. So if you're not at all familiar with cluster algebras, there's some algebra generated by generators that are in bijection with the rays of my fan. Okay? So if you have a refinement relation among the fans, there's an inclusion relation in the other direction among the rays. Now, again, if you're like me, I don't think that quickly in a talk. So if you haven't thought this through before, let's actually go to a picture quickly. But here's my two fans. Here's my one fan, first of all. This was the finer fan. And I'm just drawing dots where the rays are. Now remember, right, we had a sphere, we intersected, so the points in the plane are like points in the sphere, and then those mean rays. So I'm really drawing dots where the rays are. If I look at the red fan, the coarser fan, there are fewer rays. So these three rays, when I coarsen the fan, they just disappear. All right, so back to what we were talking about. There's this inclusion. So you might think completely naively, which is how I usually think and then hope it works. You might think, I've got this inclusion of rays, and the rays are bijection with generators. What if I, sort of make the corresponding map from generators of one algebra to generators of another? Could that possibly, be an inclusion? Could it be a map of rings? Is it possible? And it turns out that in cases, I don't have a general proof of this, but in all the cases I've checked, this works in finite type. And I can check some infinite cases. So, there's this natural injective map on cluster variables, and it extends to an embedding of the cluster algebra for the coarser fan into the cluster algebra for the finer fan. It works. And you have to deal correctly with coefficients. You have to make the map preserve G vectors, and if you know what G vectors are, you'll probably that might mean something to you. Okay, but I guess the point really is close algebraic relationships between different cluster algebras of the same rank. This is surprising a priori. They just really seem like different beasts, but it turns out, at least in these finite cases, and at least as far as I've checked, I think it's going to be true in general. Turns out that one kind of cluster algebra is a sub-algebra, or sub-ring, I guess I should say. And again, the reason that you would think to write this down is because you might think about mutation-linear maps. So, okay. I also wanted to say a few words about the lattice theory here. So, you have this fan, Cambrian fan, you could say, or a G-vector fan. If you like, just think of the normal fan, the usual icosahedron, and if you do that in sort of a fairly standard way, we could be talking about the Tamari lattice theory. So you can partially order the maximal cones of that fan in a certain way, and if you do that, you get the Cambrian fan. The other way to think about it, besides as a partial order on maximal cones of a fan, is that it's a lattice quotient, and it's also a sublattice of the weak order on the finite Cox degree. Remember, to our exchange matrix, we associate a Cox degree. So, one way to show that this refinement of fans works, using a little bit of general tools from the lattice theory, is to show that actually there's a lattice map between different Cambrian lattices. So you have the Cambrian lattice for the finer fan, you have a surjective lattice homomorphism onto the Cambrian lattice for the coarser fan. And this happens, this I can actually prove for all finite type, this happens in all finite type whenever you have the domination relation. Okay, and here's just a picture of how this looks. Now there's a whole lot of background about what lattice congruences look like that we won't talk about, but except for one thing, in a lattice congruence, maybe two things. In a lattice congruence on a finite lattice, congruence classes are intervals. So if you're putting a congruence on a lattice, and you're going to be basically decomposing it into intervals. And the other piece is that once you do that, to take the lattice quotient, you can do it purely combinatorially. You can look at the subposet induced by bottom elements of intervals. And that's what's happening here. So this is what you might call maybe a B3 Tamari lattice. And if you put, and there's some conditions, you can't just take any decomposition intervals, but this is a lattice congruence. And if you take bottom elements of intervals, you get the type A Tamari lattice. And this works in general. Right. Again, just to sort of, because this is sort of off the mainstream of the topic, but is it possible that something like that's happening, not just on the level of Cambrian lattices, which are sort of a small part of weak orders? Is it possible something like this is happening on the whole weak order? And yes, in fact, it is. So you can prove this fact about lattice homomorphisms between Cambrian lattices by showing that there are surjective lattice homomorphisms between weak orders. So the theorem is that if you have two finite Coxeter systems, and there's a domination relation. Maybe I'll interrupt the theorem to make a definition. Domination really just means that you're going to take Coxeter diagrams and you'll decrease labels, or maybe erase edges completely. Okay? But whenever that happens, then there's actually a surjective lattice homomorphism from the weak order on the bigger Coxeter group to the weak order on the smaller. Okay, and here's another example of this. I always have to point this out, because I don't want to be misunderstood. It's really easy to think that like S3 would be somehow inside B3. That's just sort of, you know, the obvious thing. But this is not that. This is S4, the weak order on S4 sitting inside the weak order on S4 sitting inside the weak order on B3 as a lattice quotient. This will probably be the last thing I'll talk about. If people want to talk about this in terms of marked surfaces in the sense of Lamine, Shapiro, and Thurston, I'd be happy to tell you about that sometime afterwards. But so there are these icosahedra, and there are generalized icosahedra, one for each finite type of root system. But affine things are the next nicest thing after finite things, and you could ask, do similar nice things happen for affine? First of all, is there an affine icosahedron? So I think the answer is sort of yes, sort of. We know what affine icosahedron's dual fan should look like. So if you had an affine icosahedron, what should its dual fan look like? I could tell you that sort of in two different ways, just like there's really two sort of root or weight ways of making the finite type icosahedra. So in joint work with David Spire, we're working on sort of a Cambrian model, which the cluster algorithm people might say is a G-vector model for an affine icosahedron fan. And in joint work with Salvatore Stella, working on an almost positive roots model of the affine icosahedron fan, and of course it should be the same fan. And I think that in this case also we're going to have these nice refinement relations. So if I start with an exchange matrix of affine type, acyclic exchange matrix of affine type, and put a refinement relation, move to something that it dominates by decreasing some entries. Well, necessarily I'll go to something that's a finite type, but there will be a refinement relation among the fans. Let me just go to a picture here. So this is a fan that's associated to, I guess, B2 tilde. And if I decrease, which one am I going to decrease? I think it's that 2 is going to be decreased. Then I'm going to end up with a finite, that was the other 2. Okay. If I decrease that 2, I'm going to end up with an exchange matrix of type B3, but there is, again, a refinement relation among those. I think this is a good place to stop. The only last thing I want to say about triangulated surfaces is that one really cool triangulated surface is the 4 times punctured sphere. And if at this conference you should happen to meet any graduate student from North Carolina State, any current graduate student from North Carolina State, you should ask them to tell you about the 4 times punctured sphere. And if they don't, so you should ask them if they work on the 4 times punctured sphere. If they say yes, if she says yes, then you should ask her to, if he says no, then you should ask him about combinatorial Hopf alphas. Maybe that's a good place to start. Questions?
Is there some sort of limit you can take as you send some of your edge weights to infinity?
I wondered about that. Some sort of universal rank 2. Yeah. You know, I remember wondering about that, and I don't remember what I came up with. I think I decided. Okay. So in the, we want to talk about mutation fan more than Coxeter, right?
Right.
So in the rank 2 case, you lose this. So I said we're going to be sort of in the well-behaved case. Rank 2 wild types are, well, they're well-behaved, but actually the refinement relations don't work anymore. You get this big open cone, and then it doesn't work anymore. So there's not,
Before we, there's another,
Nope.
from another Nathan.
Yes. So I mean, you no longer have a lattice in the affine types, but do you expect that relation between the weak orders, is there some sort of relation to hold true still?
So there is, the problem is that, so there's still a Cambrian semi-lattice, and there's still a weak order, but it's not gonna cover the entire mutation band. So the work that David and I have been doing is to, sort of, we basically put one Cambrian fan on the bottom and sort of an antipodal and opposite-oriented Cambrian fan on the top, and they glue together to get the whole thing. So it's not, I would love to know how the lattice, you know, if there's something bigger than weak order that includes all this stuff.